Yeah, thank you for the intro. Hi, everyone. I'm Andrew, and I'm here to present to you our Virtual Creatures project alongside Carol, Efe, and Anoop. So we're working on basically an evolutionary algorithm for robotic design, as was stated, and we'll just get the rest of our team here, and then let's get into the background.
So from the dawn of civilization, humanity has been looking for more and more efficient ways of locomotion, of moving stuff from point A to point B. And nature has been at this for way longer than us. And it seems to be very good at generating these very interesting, unique creatures that perform these different functions. So what we're going to be doing today is that we're going to discuss how we used evolutionary algorithms, as well as some other algorithms, to generate creatures similar to how Karl Sims did in his 1994 paper called Evolving Virtual Creatures. We're going to talk about combining reinforcement learning, which is a more modern and efficient algorithm to generate creature brains, and how we combine these to create interesting forms of locomotion. So there's many different applications of this project. So you could look at nanomedicine, such as proteins and how they move along different structures and protein motion. NASA's used evolutionary algorithms to generate antennas with the minimum number of amount of material possible. We have drone evolution, designing and controlling drones. We've also got designing and controlling walking creatures that might be going on off-road environments. And the applications of this virtual creature system is just very vast.
So we can also look at a couple of results from the original paper. We've got some very cool paddling motion seen here for the swimming environment, as well as some various types of walking motion, including some rowing and a worm-like thing. And then we've even got more complex mental behavior in target chasing, where we're going towards a vector position that's variable. We've also got some re-implementations of this work through something called the 3D virtual creatures evolution. And this is one of their kind of prime evolutions, which is the end-over-end worm. It kind of has a similar worm-like structure, but it's been discontinued. So what we're kind of working on is making our program more accessible, public, and just generally updated with modern technology. So let's get into this. What's our algorithmic basis? How are we tackling this issue?
The main crux of this project is an evolutionary algorithm. So we're going to be starting off with an initial population of, in our case, creatures, and testing them to see which ones are best at going, in this case, swimming. And we're going to be keeping the best ones, getting rid of all the rest, and mutating and crossovering the creatures that are the best in each generation to make it so that the next generation is incrementally better. Over time, the fitness is going to converge on a certain value, and we're going to receive our final, essentially, locomotion method, our perfect creature.
So here's how we've actually implemented this. For the first generation, we randomly generate a batch of 300 creatures, which you can see here. Then we evaluate their fitness, which in our case is their displacement. This is the reward that they're trying to maximize. Lastly, we keep the top 20% of the creatures, we kill the rest, and we mutate their genotypes. Note that the number of offspring of a creature is proportional to its fitness. So the most successful creatures make the most children. Then just keep repeating this process. We generate the phenotypes, we evaluate the fitness, and we select and mutate the genotypes. Finally, we stop the simulation once the fitness begins to plateau.
So some background information on reinforcement learning. So reinforcement learning works by having a learning agent interact with an environment. The agent gives an action to the environment and observes how it responds with its current state and reward. And the agent then chooses an action to take next that maximizes the reward and sends that action to the environment. So in this feedback loop, the algorithm learns from its own mistakes without the use of a data set.
And there have been plenty cool works done with reinforcement learning. We've got some awesome results from DeepMind in terms of locomotion. We've got some cool results from OpenAI involving hide and seek, where we have agents competing with each other to get better reward. We've got fantastic board gaming engines in terms of AlphaZero. And then you've got a more recent paper in soccer playing robots, where the robots not only learn to move their own bodies around and not fall over, but also control a ball against an opponent. So overall, the kind of really advanced behavior that can come out of reinforcement learning and the lack of a data set means that we're able to most likely use this algorithm to augment what came from our past work. So let's get into that. How are we actually doing this in Unity? Well, first of all, we have our combined algorithm. And what this is it's basically an evolutionary algorithm where we look at our morphological changes, going from something quite simple into something more complicated and efficient. And then we basically remove the entire brain and replace it with a reinforcement learning agent. This is to be implemented. Our project for this year was implementing the most hard to prototype part, which is the evolutionary algorithms written entirely in C#. There are plenty of Python libraries for reinforcement learning, and those connect directly into Unity. So we've left most of this as it's architecturally there, but it hasn't been trained yet. But to explain it, it would be basically a very similar multi-layer perceptron that works according to something like a policy gradient or along those lines. Our simulation and reward are relatively straightforward. We're trying to optimize for kind of efficiency of our app. So we've done a approximate linear fluid drag using the velocity of each face, the normal of the face, as well as some coefficients for drag, density, and surface area. Our fitness function has been adapted to an RL context by having it be a per frame reward. This is done by looking at the displacement of the center of mass with the dot product of the direction of travel. So this keeps the creatures kind of going in a set direction.
So how do we actually represent these creatures? So what we have is we have a set of two different, essentially our parameters, which is our genotype, as well as the physical representation of creatures, which is part of the phenotype. So we have the system of nodes and edges, which represent this the parameters of the creature. Each node represents a segment, and each edge represents the essentially the muscles and the connection between segments. We have a neural structure as well, along with this creature, where we have different neurons which take inputs either from the environment or from other neurons, and their outputs feed into essentially what strength each muscle is going to have and if it's going to contract or relax.
We also have a mutation process for these graphs. It's in 5 different steps. We first start off by mutating the parameters of each node. So this could be making a segment slightly larger, or maybe changing its color or its shape. Then we add in a new node to the graph. This is disconnected at first, and it kind of allows our creature to grow in size and change its morphology. Then we add in new connections. So we basically mutate our existing connections parameters. We can change the orientation of a part or change its position on the creature, all that stuff. Then we retarget our connections. Children are passed around, parents are passed around, and different parts are connected in different ways. And then finally, we do garbage collection. We don't want the graph to topologically expand into infinity, and so we just prune it down. This process is done for both the physical side of things and the neurological side of things.
Each running of our algorithm, each time we start a simulation, is going to generate one creature. So that is what it's going to eventually converge to. The fact this is going to converge to is it's going to be one creature. But as we run this multiple different times, different starting conditions, different mutations end up leading to very diverse and different types of locomotion, different creatures. And as you can see here, that there is, it's very good at exploring the space of all these different types of motion in either swimming or walking.
So let's get into those results.
Yeah, so what we can see here are some of the interesting walking creatures we obtained. These creatures on the top use 2 segments that self-intersect to push themselves forwards, which is really interesting because it's learned to effectively use oscillatory motion to propel itself. And it's a surprisingly simple design. Like we expected to see legs or slithering appendages, but it just traded pieces self-intersection, which is effective, but we think it's a bit too simple. So we're going to add a constraint to block self-intersection to get some more diverse creatures in the future.
Now we're going to look at creatures evolved in swimming environments. The creatures here converge toward a one body and 2 limbs that act as paddles design. They move in a periodic time asymmetric movement, which means that going forward looks different from going backwards, and this is necessary because if they move in a time symmetric movement, then they won't be able to go forward. And since the segments can self-intersect, the creature moves by first tucking one paddle into his body and using the other paddle to push, and then tucking in the other paddle and then using the first paddle to push. And here is a showcase of the pink paddle creature with the one body, 2 paddle design. And here is a fish creature which has a similar design, but the body has multiple segments which make it move in a sine wave-like motion. Both the pink paddler and the fish have the periodic time asymmetric movement, which is good. So we were able to get fitness graphs for the creatures which measure fitness over generations. Let's take a look at those. So for the purple paddler's fitness graph, the best creature's fitness goes up as they evolve creatures that make them go farther. The medium creature fitness goes up a bit, and the worst creature a lot of the time is a mutation of the best creature, and it makes them go backwards very fast. So, and then the fitness plateauing near the end means the creatures are converging toward an optimal design. And here is a creature that evolved non-oscillatory motion. For oscillatory creatures, note the longer time to converge to a higher maximum fitness. But the non-oscillatory single pusher reached a lower maximum fitness very quickly and is stuck in a local minimum. This creature was able to push itself forward once, but it can't move again. Our code currently doesn't have a method to account for this, so we'll be fixing this in the future. And here is another non-oscillatory creature with similar data.
So yeah, as was mentioned, there's a lot of potential for next steps. We're first going to try and fix that self-intersection via a repulsive force when the parts intersect. Then we'd like to add some extra joint types. Right now, we're only working with fixed joints or a hinge joint. So we don't have motion for multiple axes, that might be limiting our paddling motion. We're of course going to implement that reinforcement learning section. And then for the future, there's a lot of potential with connecting this with more robotic applications in the real world. The idea is to connect it with ROS and Isaac Sim, which allows to simulate tons of these creatures in rapid parallelized form. And you can see a GIF of that in the corner. And then finally, I hope you guys would like to use this app to create some stuff. So we're going to try and publish this as a usable app. And to do so, you can join here for more updates. And thank you for listening to the presentation, and we're open for any questions. Okay, let's see, the crossover step we're looking at. Let's see, so that was a step described in the original paper. The way it roughly works is, so you see how the creature's kind of created out of a bunch of different segments. What we do for this is the two parents will be chosen with their own respective graphs, and then the graph will be cut at some point and then spliced together based on some criteria. We didn't look too much into that step as we were mainly focusing on getting standard mutation down, but we already have a 5-step repeated process. There are so many failure cases for this, it is insane. But we've gotten this working. Next steps for the future, absolutely working on crossover. Okay, so we got a question here. How do we find the original paper? This was just found on YouTube, honestly. There was a video made a couple years after, because this was in 1994, so there was no YouTube. But after that, the work of Karl Sims was kind of collated into a video with some pretty funny, David Attenborough style, notation over everything. And it showed some pretty cool creatures. They had a swimming environment, walking, as well as jumping and competing for a block. So that was really interesting. We're looking to add some of those things. And then pivot back to Tame's question, how's crossover different than mutation? Crossover kind of lets you have two parents. Oh yeah, you can talk about it. Go ahead, Efe.
Yeah, so the reason why crossover is quite popular in most evolutionary algorithms is because it's able to increase the diversity inside of a set. Essentially, by having two different parents and combining them together, you can have hopefully the good characteristics of both. So for example, say a creature has lots of paddles that it's swimming with, and one creature has a tail. A crossover might be combining those and creating something with two paddles and a tail. Unfortunately, so with just standard mutation, what we're doing is that there is no combining of creatures together. You're only you're mutating one creature to create more steps than that. It generally tends to be quite effective. This mutation is quite effective as well. But if we can get crossover working, we would like to have a look at that in the future.
Yeah, and I see. Let's see. What kind of qualifications do you guys look for prospective group members? Well, this is our first year running this project, and it's actually my first year at UTMIST, so I'm very thankful to have this fantastic opportunity. I'd definitely like to continue this next year. We've got a lot of next steps possible with ROS and making the app, published, so we can look out for that. I think developer applications open in August, so I'll be putting out probably a revised project statement, and you guys can join the UTMIST Discord server to get more updates on that. But generally qualifications, I'd say a good amount of experience in this stuff. We're working with not only Unity, but also a lot of C# and we're re-implementing algorithm basically from scratch. We don't have PyTorch, we don't have TensorFlow. It is 5,000 lines of pure C# code. We started from the basics. So if we're going to create this thing, you need to be quite capable with really understanding the depths of this stuff. It's really fun as a result. It's a bit laborious and it's a little bit different from other projects, but it's very exciting. But yeah, other kinds of joints. I mean, the original paper had like a really long spiel about joints. It was around 20 different types, and a lot of them don't even appear on the internet. So that was something we kind of wrestled with. We ended up going to just the hinge joints for now, but some other types that were listed involved certain twisting and bending motions, universal joints, as well as constrained joints. So, we're still looking into those. Applications in robotics. Let's see. So the idea for that is basically shifting from, the kind of segments and blocks that we have towards something that could be buildable in robotics. There have been some papers on this, like kind of building a universal descriptive language for robotics and creatures and then evolving within that language. That's definitely like some potential because, let's say we're looking at a Roomba that needs to go around a house, clean different things, get under different obstacles. We could work with our lovely little cylinder that we have, or just give creature evolving a shot. Perhaps we'll evolve something quite efficient. We could add in different parts of the reward, like conserve energy, or be able to get under the couch, but also above this certain section. There's all kinds of potential for that. And there's also a couple other papers we were looking at. One interesting pathway was looking into muscle fatigue. So kind of adding in simulated muscles to get everything really smoothly operating. So that's some other pathways. Is this embodied intelligence? Well, okay, I've not heard of a proper definition of embodied intelligence, but if we take it to be an AI involving within a body, then I guess in a sense, because you could argue that regular reinforcement learning, it's already sort of embodied. It's learning in an environment to maximize a task. Like that hide and seek robot, it's able to move around the entire environment perfectly fine, and it just doesn't change its form. So this is a bit like that. The evolutionary step is definitely not as precise or expandable as the reinforcement learning. It's not a giant MLP network. It's actually a very idiosyncratic style of 22 different distinct neurons. So there's a bit of a big divorce between the field of EA in this paper and the field of RL in this paper. So it's a different combined system, but is it embodied intelligence? I'd say most likely. It's an interesting form of it. Yeah, I think that's all the questions. Let me know if I missed anything.